Hello everyone, and welcome to my presentation. So today I will be discussing the implementation of LeNet Inference Engine on an FPGA for the MNIST digit recognition. My name is Mukesh Dokala, and I'm currently a student at San Jose State University. And this project involves designing and optimizing a hardware implementation of LeNet 5, so which is one of the most convolutional neural network architecture. And this is used to recognize the handwritten digits from the MNIST dataset. Let's dive into the details. Coming to the introduction. So the project introduction starts with the LeNet 5 overview. So this is a groundbreaking neural network architecture, so which is particularly designed for the image classification task. So it processes among 28 into 28 MNIST digits and resized into 32 into 32 images. So which is done by series of convolution pooling and fully connected layers to classify digits from 0 to 9. Then the MNIST dataset is widely used benchmark dataset, so which contains of approximately 70,000 grayscale images, in which 60,000 are training samples and 10,000 are testing samples. And why we are using MNIST dataset here? So as I said, it is an ideal dataset for testing the performance of machine learning modules. So here, uh, this is a widely used benchmark dataset for handwritten digit recognition. And as I said, so it has 70,000 grayscales in which there are 60,000 training samples and 10,000 testing samples. So this project uses LeNet 5 on FPGA hardware to achieve high accuracy with optimal resource utilization. So the objective of this project is to analyze how well the model performs when implemented on hardware. Coming to the methodology. So firstly, we'll discuss about the tools we use. So for this implementation, we use Vitis HLS, which is a high-level synthesis tool, so that enables the programming FPGAs using C or C++ or OpenCL. And the primary goal of this project was to balance speed, power efficiency, accuracy in hardware. So the FPGAs are ideal for such tasks because they allow parallel processing, pipelining, and customization of hardware to meet performance requirements. So by designing and optimizing the hardware implementation of LeNet 5, we aim to achieve efficient resource utilization. So, and all these are done without compromising the accuracy of the model. And this is a design overview of the project. So firstly, we'll discuss about the LeNet architecture. So coming to the LeNet architecture, so the LeNet 5 architecture consists of three main types of layers. The first thing is convolution layer, so which extract low and high level features from the input images. And the next thing is pooling layers, so which reduces the dimensions of the data while retaining the most important features. And the last one is fully connected layers. So in this, which perform classification using the softmax functions to determine the digits. So overall, to optimizing the performance on the FPGA, we used half precision floating point arithmetic to strike a balance between computational accuracy and hardware efficiency. Additionally, we have implemented a pipelining and memory hierarchy optimizations to minimize the latency and the maximize throughput. These design decisions were crucial for achieving our performance goals. As I said, these are the hardware optimizations where we use the half precision floating point arithmetic and we use the pipelining for the enhanced throughput. And this is the memory hierarchy. So in the memory hierarchy, we have registers, on-chip memory, and the external memory. And coming to the key modules of this. So the most critical component is the convolutional module, which takes a 3 into 3 patch of the input and a kernel. So this is which applies a bias and computes the output using the MAC operations. The MAC operations is nothing but the multiply accumulate operations. To optimize this module, so we implemented a feature called zero skipping. So what has done in zero skipping is this skips unnecessary computations when the input value is 0. And we also introduced the double buffering. The doubling buffering is done to ensure continuous data flow between computations and the memory. Finally, we have designed a MAC pipeline to perform calculations efficiently using the IEEE 754 2008 half precision floating point arithmetic. These optimizations help improve the module speed and reduce resource coverage. Sorry, the resource usage. And let's move on to the results of our implementation. Firstly, let's talk about the training performance. The training accuracy increased steadily, reaching the 99% by the 10th epoch. At the same time, validation accuracy stabilized at the 98.62%. So this indicates that the model is generalized well without overfitting. Additionally, the final test accuracy on the unseen data was 98.69%. So this demonstrates that the robustness of the implementation. In terms of losses, the validation loss stabilized at 0.0459. So this ensures that the further supporting the model's efficiency. So coming to the resource utilization. And the 16-bit floating point implementation achieved a balance between the accuracy, speed, and resource usage. So this can be told by it has delivered a 310 microseconds of latency, the total power consumption of 350 microwatts. So compared to the 8-bit and 32 floating point implementation, the 16-bit design proved the optimal trade-off between the accuracy and hardware constraints. So these are some of the results. So first thing is the accuracy graph, so which tells us about the. So this is the training accuracy, which we can see that it is steadily increased, so reaching 99% at epoch 10. And next one is the validation accuracy. So it has achieved a 98.62%, demonstrating robust generalization with minimal overfitting. So the convergence was rapid within the first 5 epochs, but the validation accuracy stabilized thereafter. So this is the validation progress. In the validation progress, as you can see that, so these are the validation progress for epoch. So this is the validation progress for epoch 1 to epoch 10. So as you can see that the accuracy loss, value accuracy, so value loss. So everything from the epoch 1 to epoch 10. So the final test accuracy is the 98.69% here. And coming to the conclusions. To conclude, this project successfully implemented a hardware optimized version of LeNet 5 on FGPA for MNIST digit recognition. The implementation achieved a high test accuracy of 98.69%, demonstrating the effectiveness of the design. And key optimizations like pipelining, double buffering, and the use of 16-bit floating point arithmetic. So this all these things enable the model to perform efficiently with minimum resource usage. And looking ahead, there is a potential to optimization further by exploring 8-bit into the arithmetic, which could reduce power consumption even more. Additionally, the design can be extended to handle more complex datasets or larger models. So this makes a way for FPGA-based deep learning in real-world applications. And that's it. This is the project. So thank you.